it is time for us to talk about energy. So, energy can actually be present in several different forms. We have sound, light, electrical energy, but we're going to be focusing on energy in the form of motion and energy due to an object's position. So, a general explanation for energy is simply the ability to do work. Now, if we don't understand what work is, then that explanation doesn't do us any good. So, let's just review. Work is force times displacement. We have some force that acts along the same axis as an object's displacement. And so we take the product of those two values, and that's going to tell us how much work was performed. Now, sometimes people define energy as stored up work, and that is also an acceptable explanation. Now, a lot of times the way that people use science words in just everyday conversation are incorrect. And so we get some incorrect assumptions and understanding of words. But fortunately, in this particular case, a lot of times when people talk about work and energy, we actually hear them in a correct application. So, for example, if somebody says that they can't go mow the lawn today because they just don't have the energy to do that, that would actually be a correct representation of the relationship between work and energy. So, in order for somebody to have the ability to go and perform that physical work of pushing the lawnmower across the yard, they would need to have energy available in order to perform that physical work. And so when we say stored up work or the ability to do work, we mean something like that. Now, when we talk about work and energy, we talk about units. We say this is the variable, here's what it means, and here's what it's measured in. So when we learned about work, we said work was force times distance. That gave us a Newton meter. And we said, hey, instead of calling it a Newton meter, we're just going to rename it and we're going to call it a joule. Well, if you look here, the unit for energy is also a joule. And so what we have learned through previous conversations in physics is that variables or values or words that are measured in the same unit are usually interchangeable. They are synonymous somehow. So when we talk about work and energy, they're both measured in joules. That means that they are somehow synonymous. Now, for us to say that energy is work, to say that energy is equal to work, would actually be an incorrect statement. Yes, they are both measured in joules, but work is not energy. So what I have here is this little symbol, and it's not an equal sign. It's a little wavy that makes it more of an approximation kind of sign. So there's some sort of relationship between work and energy. They are not exactly the same thing. We are going to learn what that relationship is and why is it that we can measure both of them in joules. But we're going to need more information to understand that relationship correctly. And so we're going to save that explanation for a later lesson. But for right now, work is in joules, energy is in joules. Energy is the ability to do work, or some people call it stored up work. And so we're going to move forward with that main idea. Now we're going to talk about potential energy, and we're going to talk about kinetic energy in more detail. But potential energy is going to be expressed for us as a capital P, capital E, P for potential, E for energy, and that is going to be equal to mgh. And so I have some potential energy in this example here. I have a basketball that is sitting on a spring, and the spring has been compressed. So I actually have potential energy in two different parts of this example. I have potential energy stored up in the spring because it has been compressed, and I have potential energy stored up in the ball as it sits on top of the spring. So we're going to come back and we're going to look at this example again here in just a moment when we talk about potential energy in a little bit more detail. We're also going to talk about kinetic energy. And so we are going to write capital A, capital E for kinetic energy. Now, different texts, different online resources may choose to use some different symbols besides PE and KE. But in this class, we're going to keep it really simple. E is for energy, K is for kinetic, P is for potential, okay? This is going to be equal to 1/2 mv squared. And so we can see here in this picture, the spring has been released. It is now showing us that kinetic energy because it is now moving. That basketball is flying through the air, and so that is now going to have kinetic energy. And again, we'll talk about that again when we get to the specifics one at a time. So for right now, let's take a little bit more time to focus on our potential energy. So potential energy could be the potential energy here in this picture stored up in the spring. We would call that spring potential energy. Spring potential energy. Or we could be talking about the potential energy stored up in this basketball. Now, let's say that the basketball wasn't sitting on a spring. Instead, let's just have it sitting on a block. Well, if this basketball is sitting on a block, guess what? It still has potential energy. So what we would say here is that the basketball has potential energy, stored up energy, simply because of its vertical position. So we would refer to this as gravitational potential energy. And so this is going to be potential energy because the basketball is currently located at some position above the ground, okay? So when we talk about potential energy in this class, maybe you can see the connection with the equation already written here, but we are not going to be talking about spring potential energy in this course. Instead, we are just going to focus on gravitational potential energy. So when we talk about the definition, we have it written that this is stored up energy that comes from position. Now, you might see some text, and you might even see in some of the questions that you'll have throughout this course that potential energy is written as GPE. If we are talking about potential energy because of the object's position, because of that vertical position, or what most of us would probably just call because of the object's height. If we are referring to the amount of energy an object has simply because it is located some vertical position above the ground, well, that's because we know that Earth has a gravitational pull that's trying to act on the object. And so that's where that stored up energy comes from. So gravitational potential energy is the potential energy that we will be referring to anytime we write PE in this course, okay? So we're going to say PE for potential energy. It is specifically gravitational potential energy. So we are going to say mass, measured in kilograms, times lowercase g for the acceleration due to gravity, which we've learned in the past. Acceleration due to gravity is negative 9.8 meters per second squared. So this will be meters per second squared. Times the height. What is that vertical position above the ground? The higher we raise the object, the more gravitational potential energy it has. The more mass of the object sitting on a shelf compared to maybe a smaller, less massive object, the more massive object is going to have a greater gravitational potential energy simply because it has more mass, even though it's located at the same height, right? These are the types of interpretations that you guys should be capable of making at this point simply based off of the mathematical equation. Now, if we were to do the algebra, we would find that a kilogram times meters per second squared times a meter is going to give me a Newton times a meter. Well, like we've learned before, instead of expressing it as a Newton meter, we're typically just going to call it a joule. So we have potential energy in joules equals mass in kilograms times gravity in meters per second squared times height in meters, okay? And so this is what we will be referring to anytime we are talking about potential energy in this course. Now I want to pause and I want to point out in previous chapters, we've made a really big deal about making sure that we are including that negative with the 9.8 meters per second squared because acceleration is a vector. The acceleration is in the downward direction, physically towards the ground. And so we've decided that that's the negative direction for our math work. When we are talking about energy, we are going to be calculating how much energy does an object have at that location. So for right now, we are simply quantifying the amount of energy available. We are not saying that this energy is oriented in one direction or another. So for all the calculations you're going to do, if you are simply saying how much potential energy does this object have at this location, you're actually not going to be using the negative. You're just going to put in that magnitude of 9.8 meters per second squared because we will not be given a direction. We are simply quantifying how much potential energy is available at this location. When we talk about kinetic energy, we said that our equation here is going to be KE, K for kinetic, E for energy, and that is set equal to 1/2 mv squared. So we are going to have mass, which is measured in kilograms, and we're going to have velocity, which is measured in meters per second. And so these are the units for the variables that we're going to substitute in. Now the equation says that we are going to square our velocity. So if we think about what that means, we are going to end up with kilograms times meters squared divided by seconds squared. Once again, that's going to give us a Newton meter, and so our kinetic energy will just be measured in joules. Remember, we said at the beginning of this lesson, energy is measured in joules, okay? All right, now it says here, kinetic energy is the energy of motion. If my object is at rest, we would say KE equals 1/2 mv squared. If it is at rest, then my velocity value is 0. Therefore, it doesn't matter what my mass is. It doesn't matter that I'm squaring it. My kinetic energy will simply come out to be 0 joules for any object that is at rest because the object is not moving, it is not in motion, does not have kinetic energy. It's as simple as that, okay? Now, if my object is moving, then whatever the velocity is, we're going to take that velocity value and we are going to plug it into our equation. So if I have an object that is moving, let's say that it's a 2 kilogram object and it's moving with a velocity of 2 meters per second. Oh no, let's change that, with 5 meters per second. So we would say that it is, let's change that up, 1/2. It's a 2 kilogram object moving at 5 meters per second. The 5 is the value that gets squared. This is velocity squared. So if it makes more sense to you to write 5 squared and then close your parentheses, sure. So then we are going to say 1/2, which honestly, guys, I would recommend that you just get in the habit of typing that as 0.5. It simply reduces the need for parentheses and makes you push less buttons in the calculator. And so we are going to get an answer of 25 joules. Now, if we have the same object, but instead of having it move at 5 meters per second, let's make it move faster. So let's have this object move 1/2 mv squared. Let's make this object move at 20 meters per second. Sure, so 20 is being squared. So we're going to put that in our calculator, 1/2 times 2 times 20 squared. So we're going to square our 20 and then we're going to multiply times 2 and then cut that in half and we get 400 joules, okay? So what we're seeing here is that if we increase our speed, that's going to increase the amount of kinetic energy that the object has. You should understand that there is a direct relationship because the equation says velocity squared. If it's an answer choice, I'm going to say it's a direct square relationship, but in general, I need you to know that velocity is directly related to kinetic energy in the sense that if I make it move faster, I'm going to have more kinetic energy. Now, it also says that if we increase the mass, so now let's go back to our original problem where we had our KE equals 1/2 mv squared. And we had a mass of 2, and then we had a velocity of 5. Well, what if we had two different objects, and they are both moving at the same speed? So instead of having a mass of 2, what if my second object was a mass of 10 kilograms, and it was moving at 5 meters per second? Well, we're going to take 1/2 times 10, and we're going to multiply that by 5 squared. And so that is going to give me 125 joules. So if I compare my object with a mass of 2 kilograms to my object with a mass of 10 kilograms, I can definitely see the more massive object has more kinetic energy. And that's what we're saying here in this second statement. So kinetic energy and mass are also directly proportional. It's a direct square for velocity. It's just a regular old direct relationship for mass. So these are just some of the things that we expect you to be able to answer if we ask you questions about these types of relationships in questions in the future, whether it gives you numbers, whether it's a math problem, or it's just a conceptual question. So make sure that you understand the meaning of these different types of energies, know them by definition, be familiar with the equation, know how to substitute in the numbers. And then it says here, it takes more force to move the more massive object. Guys, I cannot stress enough, old information is going to continue to show up in the remainder of the topics that we discuss. So we should now understand that force is responsible for that acceleration. If I'm trying to change the amount of kinetic energy for an individual object, then it must be because I'm trying to change the velocity. If I'm trying to change the velocity, that means the object experienced an acceleration, which must mean that a force was required to act on it to change that velocity. So just simply being able to connect the dots here is going to continue to be super important for all of the concepts that we have covered.